Welcome to the presentation about modified dolomite for phosphate adsorption in aqueous solution. The summary of this presentation is introduction, methodology, results and discussions, and conclusions. In the introduction, we are going to talk about phosphate problems in the environment and how to reduce its impact with use of dolomite. So, the increase in the concentration of phosphate in the water bodies causes eutrophication in the system. In this phenomena occurs the decrease of oxygen concentration and therefore the death of aquatic organisms occurs. The principal sources of phosphate in the effluents can originate from domestic activities, agriculture, and the industry. Several studies use adsorption to remove phosphate from water bodies. It is one of the most used processes due to has easy operation, low cost, and it is an efficient process. So, adsorption is a surface phenomenon that involves increasing the concentration of the contaminant on the solid surface. In the adsorption process, the efficiency of the contaminant removal can be influenced by several factors, such as particle size, surface area, and pore size. Exist different materials that can be used as adsorbent solids. The minerals such as dolomite, that is a sedimentary metamorphic rock, is considered an economically suitable alternative as adsorbent solid. Due to dolomite is a carbonate of calcium and magnesium, it has high crystallinity and alkaline nature, making it a promissory material for immobilization of acid contaminants like phosphate. However, dolomite has low specific surface area and pore size, which are limiting factors for adsorption process. Therefore, in this work, the question was, how can we improve the physicochemical properties of dolomite to increase the efficiency in phosphate removal? As solution to this problem, we propose modify the dolomite through both physical and chemical methods such as calcination, ultrasound, layer double hydroxy synthesis LDH before application for phosphate adsorption. So, to solve this problem, the following methodology was applied. As adsorbent solids were used, raw dolomite and calcined dolomite at 800 degrees Celsius. We applied techniques such as nitrogen adsorption desorption and X-ray diffraction to characterize the materials. Raw dolomite also was modified with 30 minutes with ultrasound bath. The chemical modification of dolomite was carried out with aluminum salt to obtain a larger double hydroxide. The effect of pH, solid dosage, and contact time were studied to evaluate phosphate absorption capacity on each modified solid from dolomite. The pH effect was evaluated at different pH values under stirring, and the final concentration of phosphate in the solution was analyzed using an spectrophotometer at 420 nanometers. The effect of solid dosage was carried out at different dosage of solids. For this test, the pH was used according to the best results obtained in the pH study. contact time experiments also were performed applying the best results for pH and solid dosage experiments. Results and discussion of this work. X-ray patterns show that all solids are crystalline. In the X-ray patterns for raw and modified dolomite by physical methods, it can be seen that the solid presents several diffraction peaks that have been attributed to carbonate phase and calcined phase. It is possible to observe that in the calcined sample the intensity of the peaks decrease. It is maybe caused by thermal decomposition of dolomite. In the ultrasound sample also the intensity of the peaks decrease, but in this case it is maybe caused by cavitation effect of the ultrasound method. To the chemical modification, it can be seen that the structure is different when compared with other solids. The solid has three main reflections that correspond to diffraction band planes at 003, 006, and 009, and represents the separation between layers that characteristics of LDH. The table shows the nitrogen adsorption-desorption results. The characterization results showed that all methods improve the dolomite physicochemical properties. It can be seen that the specific surface area of LDH obtained from dolomite was 34 times greater than raw dolomite. To dolomite modified with ultrasound bath was 3.3 times greater than raw dolomite, and the surface area of calcined dolomite was 2.7 times greater than raw dolomite. The following results show the absorption capacity of the solids for phosphate removal. The table shows the best parameters obtained for each solid. The absorption results showed 70 and 90% of phosphate removal on raw and calcined dolomite, respectively, under the experimental conditions of 11th of pH, 3 grams of solid dosage, and 60 minutes of contact time. The best operational parameters for dolomite treated with ultrasound bath were 9 of pH, 1.7 grams of solid dosage, and 55 minutes of contact time, with about 90% of phosphate removal. The LDH obtained from dolomite allowed above 94% of phosphate removal at natural pH, 0.2 grams of solid dosage, and 50 minutes of contact time. So the conclusions of this work are: characterization results showed that all methods improve the dolomite's physicochemical properties according to the following order: LDH, ultrasound, calcined dolomite, and raw dolomite. Results showed that raw dolomite was modified, exhibiting enhanced surface area. However, chemical modification to obtain LDH from dolomite showed improved physicochemical properties, resulting in higher absorption capacity, making it a more promising material for use in the immobilization of phosphate. Thanks for your attention.